If you look at a map of the Earth, you'll see this very familiar arrangement of continents. But if we were to remove the oceans from this map and have a look at the bottom of the ocean floor, or on the ocean floor, you'll see that there are these different, what appear to be sort of lines extending between and around many of the continents. This property of the Earth divides it up into what we call plates. So the Earth is not just one uniform crust. There are different plates that make up the Earth's surface. And it's the boundaries of those plates that we're going to be looking at now. It's this arrangement of plates and what occurs at those boundaries that gives us what we term plate tectonics. And those boundaries are very actively tectonically, meaning that they move. They're very volcanic and they are mobile. The Earth is not a static system of just a solid crust. Those plates move around, and you can see here the arrows representing how they move around. You can see that the plate that we are standing on, or most of us are standing on if you're in Australia, is moving north, whereas the Eurasian plate is moving sort of southeast. And so there's some sort of collision going on there, which may produce something you've probably heard of before, which we'll look at a little later on. And plates have been moving throughout geological history, as this animation shows of the breakup of the supercontinent Gondwana, which started about 200 million years ago and resulted in the present-day positions of the continents around the globe. Okay, so let's have a look at these plate components. What are plates made up of? Well, the crust is divided into these plates. So we know that the crust is a solid part of the Earth, one of the solid Earth layers. So the crust is the outer layer, and there are two types of crust. There's continental crust and there's oceanic crust. The oceanic crust, underneath the Earth's ocean, is about 5 to 10 kilometres thick, and the continental crust can range between 20 to 70 kilometres thick. It differs obviously, but shows that there's a major difference between those two types of crust. Now, the average density of continental rocks, you can see there, is about 2,700 grams per cubic metre. And its composition is similar to granite. And I'll show you what that looks like. Here is a sample of granite. So here's your second rock. Granite, meet the class, class, meet granite. Okay, oceanic crust is much thinner. It has a much higher density, or slightly higher density of 3,000 kilograms per cubic metres. And its composition is similar to that rock that we saw before, basalt. Now, basalt, is what makes up the ocean floor. So that oceanic crust is made up of basalt. It's very dense. Continental crust is like granite, and it's less dense. So that's one of the reasons why continental crust occurs above oceanic crust. Okay, so continental crust is thinner and it's more dense, and so sits lower on the Earth's surface than continental crust. Now, both of these things sit on top of what's known as the mantle. Okay, so on the asthenosphere. And the asthenosphere, the mantle material, is denser still at 3,400 kilometres per cubic metres. So this arrangement of different densities gives us the relative position of these different types of material on the Earth's surface and those outer layers. So the crust and the lithosphere is what makes tectonic plates, and these are solid. Okay, so you have your oceanic crust and your continental crust sitting on the lithosphere, and that's solid, so that's what we call plates. And then they float on the next layer down, which is the asthenosphere, because as we saw before, the asthenosphere is much hotter. It's still relatively solid, but it's hot enough to start to flow very slowly, And it's that flowing because of the heat, and the heat of the convection currents cause it to move around and very, very slowly, but anything solid that's on top of that moving asthenosphere is also going to move. And so that's why our plates, that's the process by which the plates on the asthenosphere, the plates on the Earth's surface move around. Now those convection currents are going to be different depending on where they occur in the upper mantle, in the asthenosphere, in the Earth, and so that's why plates move in different directions. It's just like when you heat a saucepan of water and you've got those bubbles going really rapidly in all different directions. Well, that's what's happening in the asthenosphere, in that mantle and the upper mantle in that asthenosphere. The bubbles, they're moving much more slowly, but they're occurring randomly. And so the plates that sit on top are going to move randomly as well. Now, over time, we've been able to map how those plates are moved, how those plates have moved, and we have this sort of appearance where you can see in this animation how the plates have moved around the Earth's surface over time. Now, how do we know that this has occurred? Well, very early on, hundreds of years ago, early geologists and geographers looking at the shape of the continents on the Earth saw that some of them seemed to fit together as though they were in a jigsaw puzzle. But they were located hundreds or thousands of kilometres apart. So they thought, well, how can this possibly happen? They didn't have an explanation for it, but they just noticed that some of the continents seemed to fit together quite well. With more and more evidence coming forward, particularly when geologists and paleontologists started to look at the fossil record, they noticed that some fossils occurred, some fossil types, the same animals and plants, occurred in continents that were presently hundreds or thousands of kilometres apart. So how did you get these same fossils occurring on continents that were now many kilometres apart? Now, animals perhaps could have walked, but plants don't walk and don't travel very far generally. So that was a real conundrum. And so by putting that evidence over top of this jigsaw sort of theory, then people started to think, well, perhaps once upon a time these continents were together. With more and more evidence as time went on, geologists were now able to start to date rocks. And what they were noticing was that when you looked at those, remember that one of those lines that were on the ocean floor, when people started to date the rocks away from those ocean floors, those lines on the ocean, I'll tell you their proper name in a minute, but those lines on the ocean floor, when they looked at the pattern of ages of the rocks, they noticed that the rocks closer to that line on the ocean floor were much younger than the ones further away. But it was a mirror image. So they noticed that the ones further away were the same age and they were similar distances away from that particular line on the ocean floor. And then the other way, with even more evidence, and this one's pretty cool, was they used geomagnetic reversals in these rocks. Now, what on earth does that mean? Well, did you know that the Earth's magnetic field flips around from time to time? North becomes south and south becomes north. The polarity of the Earth's magnetic field flips around. Nobody really knows why. Perhaps the Earth's core is sort of flipping over. Who knows? But it does. And we can tell because the iron minerals that are formed in the rocks, so there's iron in basalt, remember this is the stuff on the ocean floor, they could see the alignment of those iron minerals changed from time to time. Sometimes they were pointing what we would call north, and sometimes they were sort of pointing to what we would call south. Now, how can that happen? It can't. They have to always point to what we always call north. And so if they were appearing to point the different direction, that it could only mean that the polarity of the Earth is flipping around. And so in the same way where they mapped the ages of the rocks at similar distances away from that line on the ocean floor, they were able to map the flipping of those iron minerals in a similar way, equally in rocks equidistant from the central line on the ocean floor. So this little animation here shows it. So let's run this animation, and you can see that the rocks are being produced and the iron minerals are pointing in one direction. Now let's flip the polarity, and we've flipped it, and now it's pointing a different direction. But the same polarity is being recorded in those rocks as it moves away from that boundary. Now, what's happening here? Well, what's happening here, as this diagram now, as this animation shows, is that in the Earth's surface, underneath the Earth's surface, in that upper mantle in the asthenosphere, as those convection currents are turning, it's pushing those plates apart, and they're moving. And they're not only just moving, if they move apart, well, that creates a gap between those plates and has to be filled by something. What's it filled by? It's filled by basalt. So the asthenosphere, remember, is like a rock similar to basalt. Well, it rises, the basalt rises, and it creates new ocean floor. As those plates are pushed apart, new ocean floor is being created. And that's why when we measure it, it's the youngest, nearest where this is occurring. Okay, so what do we call that? Well, that's a plate boundary, and that particular plate boundary is a divergent plate boundary because the plates are moving apart, and we call that a mid-ocean ridge. So that's the first plate boundary that we're going to look at. Okay, now there are a couple of other types of boundaries. There are convergent boundaries, subduction zones and continental convergence, and there are transform boundaries, and we're going to look at each of those. Okay, so here's a good example of a mid-ocean ridge where the two plates are pulling apart. And here's a diagram showing you that, the rising of the asthenosphere, pushing apart the crust and the plates and forming new basalt in the gap that's being created. Okay, so that's what we call our mid-ocean ridge, and here's a diagram showing you all the mid-ocean ridges on the Earth's surface. Now, I mentioned that there are other types of divergent boundaries, and another one is called a rift valley. So this doesn't occur necessarily on the Earth's, in the ocean. It can occur actually in a continent, so it can split a continent apart. Same thing happens, the convection currents in the mantle and the asthenosphere push apart the plates, create a gap, and that gap has to be filled by something. Again, it's filled by material from the asthenosphere, so it's filled with basalt and creates new sea floor. And so you can see here in this animation the creation of new sea floor in what was once upon a time a continent, and you've now got new ocean occurring in what was once upon a time just a continental part of the continental crust. Where that's occurring now is the Great Rift Valley in Africa, where you can actually see it starting to pull apart. And this diagram here shows you what's happening at that Rift Valley, and this is a picture of the Rift Valley in Africa. You can see how those two sort of look pretty similar. So eventually that part of Africa will split apart, and there will be new ocean will eventually find its way into that part of Africa. Okay, let's move on to a different type of boundary. Now, a divergent boundary is where those plates are moving apart. We're now going to look at convergent boundaries, and that's where two plates are coming together. Remember, the plates move around differently depending on those convection currents. And so where two plates are coming together, there are two types. You can get what's known as a subduction zone, and the sort of most well-known subduction zone is down the west coast of South America. Now here, what you've got is oceanic crust moving towards continental crust. So the ocean floor of the Pacific and the continental crust of South America are being forced together by these plate tectonics. Now remember that oceanic crust is more dense than continental crust. So what's going to happen when they come together? Well, because the oceanic crust is denser, it's going to go underneath, and the continental crust is going to go over the top. Now what that creates is that this continental crust is then subducted down into the hotter parts of the mantle. It's going to melt. Some of that will rise up through the continental crust, melting the granite in the continental crust and creating explosive volcanoes. As we see when we look at rock types, you'll see that this stuff's pretty sticky when it's molten and creates explosive volcanoes. The other thing that's occurring is that you've got another rock type, a sedimentary rock type. As sediments are washed off continents, particles collect and they form a new rock type like sandstone, and that's scraped off onto the edge of the continent, and that tends to then build up new mountains, and that's what we have down the west coast of South America, which is the Andes. So that's a convergent plate boundary and a subduction zone. Okay, what happens when you have two plates coming together that are of similar densities? So in this case, you've got a continent and a continent coming together. And the best known one is the boundary between India and the rest of we can term Eurasia. There you've got a granite, or continental crust and continental crust coming together. They're both of similar densities, so it's unlikely one's going to go easily underneath the other. So instead, they both go up. And what's occurring at that part of the Earth's surface? Biggest mountains on the Earth. You've got the Himalayas forming because you've got those two plates coming together, and they are being forced up on this convergent zone. The last plate boundary that we'll look at, the most well known, is on the west coast of the United States, and that's known as a transform boundary. So the plates aren't moving apart and they're not directly coming together, but they're sliding past each other. And as they do, the forces that are occurring cause great earthquakes. Now, if you know, Los Angeles and much of the west coast of America is susceptible to huge earthquakes, and one day there will be a massive one. That's because you've got a plate boundary right down the coast of the western part of the United States. And this little animation shows you how those two plates over millions of years are moving, and what will the location of the different cities on the west coast of America will change over millions of years.